So if we can improve devices by finding better technologies based on quantum simulation, then I can do better quantum computing, which on the other hand then enhances the quantum simulation part that I want to do on these devices.
When Richard Feynman proposed the idea of a quantum simulator or computer in 1981, he was frustrated by the limitations of classical systems. He logically suggested that if we live in a quantum world, we need a quantum device to simulate all the interactions of particles that make up reality. An excellent example of such a transistor-choking calculation is the quantum many-body problem. Have quantum computers finally cracked it and reached the level of Feynman's original idea? And does this have anything to do with the three-body problem novel and Netflix show? Find out in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is professor at TU Dortmund University and staff scientist at the German Aerospace Center, DLR. Benedikt Fauseweh, welcome to the show.
Thank you so much for having me.
Yeah, so to quickly orient our U.S. listeners, your role at the German equivalent of NASA, right? That's
Yes.
basically how you would consider it?
Yes, absolutely. And we actually have cooperations with NASA. So, for example, at DLR, specifically at my institute, which is the Institute for Software Technology, we actually have a software agreement or a software cooperation with NASA Ames, who also work a lot with quantum computers and also have, for example, a D-Wave and NELA. So we work a lot with them as well. Yeah.
Great. Yeah, that makes it easier for people to just understand what's
Yeah,
out there.
sure. Absolutely.
So tell us how you got there real quick, because your career is interesting. You kind of started where you ended up also when it comes to being a professor, right?
Yeah, sure, absolutely. So I did my, I already in high school, I was fascinated with physics. I read these books by Stephen Hawking, and I said, I want to learn more about that. So I studied physics actually in Dortmund. And I then did my PhD back in 2016, and I was mainly working on quantum magnetic systems. So quantum magnetic systems are like a lot of qubits, but we don't have so fine-grained control over them as we would like to have. So typically they are in materials, and we want to understand what happens in these materials with these magnetic excitations. And then after finishing my PhD, I went to the Max Planck Institute in Stuttgart. There I did a lot on non-equilibrium dynamics, maybe something that we will touch today on, in superconductors. And for that time, I was also for 4 months at the University of Tokyo, learned about a lot of numerical techniques. And after that, I joined the Los Alamos National Laboratory in the US.
Mm-hmm.
And I was mainly there working also on, let's say, material systems. But at the time, we also had access to the IBM quantum computers. And we discussed in the team, hey, don't we want to do something with that? We are quantum physicists. So we want to use these devices to learn something about quantum systems. And that got me into this whole field of quantum computing and quantum simulation. And we did a few studies on the IBM machine. And then I went on to the German Aerospace Center because they were looking for people that are versed in quantum computing and quantum simulation. And there, around 2022, I started to build up a group on quantum computing applications. And just last year, in November, I started in parallel my position as a assistant professor at TU Dortmund University. So going back to my alma mater, because they also are now very interested in these quantum simulation topics. And I think you also have that in the US, that more and more universities are starting to look into this whole field of quantum computing and so on. So it's kind of the same thing that we have here in Germany.
Yeah, so you were basically taking it easy for 8 years. No, I'm kidding. That's that's very
Exactly.
impressive. Everyone listening is like, I don't know, there was a pandemic. I don't know.
Oh yeah, there was something in like that in
Yeah.
between. That's true, but
Yeah.
yeah, I agree. That was also not an easy time. I was in Los Alamos at the time, and so then we had to work from home. But in
Mhm.
the end, we got a lot of work done, so that was nice.
Yeah, I was worried that everything would stagnate, like how nothing in the lab is going to be happening, that kind of thing. Um,
Happily, I don't have to go into the lab as a theoretician. That's the nice thing for
yeah,
me.
yeah,
Yeah.
that's true. It's like anywhere there's a computer, that's my work, right?
Or anywhere there is something I can think about and write
Yep.
something on a piece of paper, right? So that's still something that I do from on a day-to-day basis. Yeah, it's really thinking about stuff and writing this down on a piece of paper. Right? So it's not always just a computer.
That's great. So at DLR, they think of the very big, right? I mean, there's nothing bigger than space,
Absolutely.
like, right? It just goes on and on and on and on. So that's as classical as it gets. But then obviously with the quantum aspect, your work deals with the very very small. So we're going to run the gamut here in the stuff we talk about.
Yes.
So one of the reasons I wanted to have you on was you wrote a paper that got published in Nature. There'll be a link in the show notes, and
Hmm.
it has a good title. It pretty much explains it clearly, so I'll say it. It's the Quantum Many-Body Simulations on Digital Quantum Computers, State of the Art and Future Challenges. So that's great.
Hmm.
Crisp title, wonderful. So for our listeners to just orient, can you explain
Hmm.
the quantum many-body problem?
Absolutely. So in you know that in quantum physics the idea is that if we look at matter, if we look at particles and so on, we realized very quickly in the last century that these particles don't behave as classical particles, but they rather behave as quantum particles. So they have properties that are at the same time wave properties and particle properties. So this is this particle wave duality. And so describing these systems of particles, for example, is on a classical level is rather easy. So if you just add one particle, the complexity of your system scales linearly with the number of particles. So if I add one more particle, I have to do one equation more, and that's it. On the other hand, if I want to do the same kind of calculations with many particles, and they are quantum in nature, then it turns out that if I just add one more particle to my problem, what typically happens is that my problem gets double as hard as it was before. It's not just one more, it's actually factor 2 or 3 or something like that.
Mm-hmm.
And this is what we call in math, we call this an exponential scaling, right? So if I add a little bit more, then the problem gets exponentially harder. And the quantum many-body problem is exactly this problem. So what I actually want to do is I want to simulate, for example, a material, for example, the cuprate superconductors, which are very relevant in high-tech applications. If I want to describe these materials, I know that they have quantum features. They are superconductors, so they are definitely quantum. But if I want to describe these 10 to the 23 particles in there, I would need an exponential amount of computing resources that would exceed all the computing resources available in the universe, so to say, if I were to simulate that classically. Yeah? So we cannot simulate this exactly on a classical computer. It's impossible. And the reason is that these particles are talking to each other, right? So the reason is that they are interacting with each other, and this makes it so hard to calculate material properties. Now, of course, there are let's say methods to treat also problems which are not so strongly interacting. Yeah, so for example, if I take a material that is very simple, like a metal, something like copper or so, or maybe some other very simple metal, then typically it turns out that these materials are not so strongly interacting. So I can just just describe them as a single particle that doesn't feel so much of the other particles, or only feels a mean field of the other particles. And then this allows me to actually make some predictions in material science. But when it comes to these quantum functional materials, these materials that really have in its fundament something that is can only be explained by a collective process that is quantum in nature, then it will be very hard for us to predict these features in physics.
So people, listeners should be familiar with this concept of every time you add a particle, you're doubling. I mean, that's the nature of qubits, right? Like in
Exactly.
theory, if you have perfect
Exactly.
qubits, you have a 100-qubit system, a 101 system would be twice as powerful, right?
Exactly.
So yeah, this is something we should already be familiar with. The other thing to key in on is you talked about how it gets out of hand, the computing resources. And of course, if we go back to 1981/1982, if you include a publication, Richard Feynman, that's the exact reason he came up with the idea of a quantum computer. He realized that to simulate this world, we need something quantum because the world is quantum. Yeah.
Exactly. You really made this very good point. Is that when Feynman realized this and said, well, if the nature is quantum, then our computers should also be quantum to be able to capture this behavior. And that's the fundamental reason why Feynman actually proposed the quantum computer, was for quantum simulation, was for exactly this reason. He said, I can't do these calculations anymore. In some cases, I can do them on a piece of paper, but in most cases, in the general case, it's very hard. And then I want to do good simulations, and that's what the quantum computer would be most useful for us, for example, in physics.
Yeah. So do you consider simulation of quantum many-body systems to be like a fulfillment of his vision in a way, right? That's
Absolutely,
the first thing I
absolutely.
thought of when I saw it.
Absolutely. I think at the time, of course, Feynman did not have such a, let's say, nuanced picture of what we could do with quantum devices as we have as of now. That's absolutely the case, but because at the time we didn't have any kind of these devices at all. And by now we kind of have a more precise picture, in the sense that we now, for example, distinguish between analog quantum simulation on the one hand and digital quantum simulation on the other hand. I think for Feynman already, this analog simulation would be something that was very much a part of his dream, because with that we can already do simulations that are out of reach for classical HPC simulations, for example. But on the other hand, the, let's say, full dream of doing any kind of simulation, this can only be done then with digital platforms, with digital quantum computing.
Yeah, can you explain a little bit the difference between the analog and digital in case people are confused?
Yeah, absolutely. So analog platforms are quantum platforms that they can be based on qubits, but the thing is that in analog platforms, I have a limited, let's say, set of control parameters, right? So I can only simulate a small a set of models on these platforms, because I don't have full control over these platforms. But they realize that, for example, let's say that time evolution of a quantum system very precisely for the given system that I can simulate on these platforms. On the other hand, digital quantum simulation really uses a quantum computer, which is universal, right? So I can implement in principle any kind of unitary action or unitary transformation on that quantum computer. But what I need to do there is I need to really discretize, for example, my time evolution into gates, and then I need to execute those gates on a quantum computer. And that is the difference between these analog and these digital platforms. Now, on the technology level, those two are oftentimes not so far apart from each other. So, for example, one of the leading platforms in analog quantum simulation are neutral atoms.
Yeah.
And there has been a lot of progress in analog quantum simulation using these neutral atoms. But by now, also these platforms are now slowly developing towards the digital approach, because they can now do more and more fine-tuned control of these neutral atoms. And this in the future is, of course, the hope that we can also do full-scale digital simulations on these platforms as well, so that we have the freedom to look at any kind of problem that we want in digital quantum simulation.
So I got to see early versions of, for example, QAero machine, and now they've come a long way since then.
Absolutely.
And we talked about it a bit on the show, but obviously not everyone listens to every episode, so I
No,
want to
sure.
make sure they had a little bit of a background. So I appreciate the explanation for them. And it's very evident that analog seems to work more in the world of simulation. You create this almost like visual representation with the qubits, and then now they are trying to, like I said, trying to create the gates and get these like very
Yes.
discrete answers. So it's sort of like we're moving from the realm of Feynman to the realm of David Deutsch, if you want.
Yeah, one can say so. I mean, Deutsch was even. I think he even made these statements before Feynman, if I'm not mistaken. I'm not so
Yeah,
sure
there's that
about
back
the
and forth, like in the late 70s, maybe he
exactly.
was thinking along those lines. Yeah.
Exactly. And then and Feynman, of course, had this physics perspective and said, "Well, I want to actually learn something about physics." And by now, I think we're moving in the same direction. That's the nice thing. It's really it shows that if I want to do general type of digital quantum simulation, I need a general purpose quantum computer, and that is what I think is the current direction that we're looking at.
Yeah.
Also technology wise, as well as let's say software wise or algorithm wise and so on, is going in that direction.
So practically now, can we talk a little bit about how analog and digital approaches differ in simulating, when we get down to the non-variational and variational approaches?
That's what I mean. Yeah, sure,
Yeah.
absolutely. So what I did in my paper is I try to find some kind of categorization in at least in digital quantum simulation.
Hmm.
And what I did is I tried to divide this into two parts. One is the, let's say, non-variational results and the variational results. And now, before we talk about this distinction, or before we talk about the details in each of these sections, we should talk about what is the distinction between the two.
Hmm.
And the distinction is in that variational methods typically have something like a quantum classical feedback loop, where what I'm actually trying to do is I define a cost function, which is, for example, let's say the energy of my system, and I want to minimize that energy because this gives me the ground state, which is for physicists the most important state of a
Hmm.
quantum system. So what I do is I do on a quantum computer what the quantum computer can do best. It can represent quantum states in a large dimensional Hilbert space. And on the other hand, I let the classical computer do what it can do best, which is minimizing functions. So what it does now is I prepare a state on a quantum computer, I measure its energy, I take that energy as input for the optimizer on a classical computer, and then this optimizer says, please adjust the following parameters in your circuit such that we can minimize the energy further. Yeah. So this is what a variational algorithm is. And it has been proposed specifically for these noisy quantum computers that we have right now, because the idea is a little bit that variational methods are intrinsically robust against noise. Because, for example, let's say I have a gate that is slightly miscalibrated, right? So I want to do a rotation by 90 degrees, and it actually does a rotation by 89 degrees or so.
Hmm.
Now, the nice thing about the variational algorithm would be it would realize, 90 degrees is not optimal. I see that. But if you change this gate now to 89 degrees, then we get the optimal energy. Yeah, so this means it's kind of robust against such small errors. And on the other hand, these variational methods then have other drawbacks, which is, for example, that at some point, if the depth of that circuit gets too deep, then we realize that we cannot optimize this circuit anymore because it's missing a gradient. The gradient goes to zero, and if the gradient goes to zero, we have no information where to go to, so to say.
Hmm.
And now, what I did in my in this paper was that I discuss the digital quantum simulation based on these variational or non-variational results. And the non-variational results is really, let's say, one of the first ideas that were proposed in order to do quantum simulation. So Feynman said, okay, we want to build this quantum computer, but he didn't argue so much mathematically why this is possible. And then Lloyd came up and said, well, if we if we have a Hamiltonian and we can do a Trotter-Suzuki decomposition of this Hamiltonian, as it's like a discretization of my Hamiltonian, then I can do the time evolution efficiently on a quantum computer. Yeah. So, and based on this so-called Trotterization, very many people looked into, okay, what can you actually do with these current day quantum computers? And they just use this approach of discretizing the time evolution and try to see how far can we get with this. So for example, how large can I make the systems and how many time steps can I do? That's essentially the two dimensions that we're looking at. This is the length of the circuit and its depth. And so there it turned out that in very many of these systems, you can get accurate results, but only if you restrict your numbers of qubits as well as the depth of the circuit that you're looking at. Yeah. I did myself a study in 2021 with these IBM devices back in Los Alamos. And there we could, for example, go up to roughly 10 qubits that we could simulate then for roughly also 10 time steps. So this
was an archive paper about that, I believe.
It's actually by now it's on quantum information in the journal Quantum Information Processing.
Great.
And so there we kind of look into this and say, okay, what can we do there in time evolution, for example? And it turns out that this was, let's say, it was working well, but you had to do a lot of work to get this done. So in the sense that if you execute these circuits without any additional pre and post processing on the IBM devices, mostly the output is 50% trash, I would say. Yeah, something like that. So what you have to do is you really have to pre and post process your data using these error mitigation methods. Yeah? And that's what we did, and we found out then you can potentially go to, for example, let's say up to 10 qubits. There are other things that you can also now do on these quantum computers without just time evolution. So, for example, one can also try to realize topological systems on these devices. So this was done, for example, on the Google Sycamore quantum processor, where they showed you can really realize, for example, the toric code on this 2D lattice, or you can look at something that we are also started to look into much more, which is called time crystals. So time crystals.
Yeah, that generated a lot of buzz.
Exactly. These time crystals generated a lot of buzz, but they are kind of interesting. And why is that the case? They are interesting because they're kind of intermediate between let's say if I choose one way to benchmark quantum computers nowadays is, for example, with quantum volume. And the way that you do this is you run a bunch of randomized circuits on your quantum computer and you measure how often do I get the right result out of this randomized circuit. Yeah? And on the other hand, what you can do is you can play around with these VQE circuits, so these variational circuits, in order to find ground states. Now, what is in between is kind of these time evolution circuits, which have a clear structure to it, but they can still go into places in the Hilbert space which are, let's say, very entangled, very difficult to describe by classical methods. And time crystals are just on the edge of this regime. So time crystals, they are, let's say, systems that you evolve in time. They're called time crystals because essentially the idea is that if you evolve the system in a time t, then the system actually, so it has some periodicity to it, then the system itself responds with something that is 2 times or 3 times this period t. So this is what we call a broken symmetry, and therefore we call it a crystal. Yeah, it's really just a fancy name.
Yeah, there isn't something that all of a sudden manifests out of it.
Absolutely not. No. It's just the idea that if time goes t and you go 2t, then you are a crystal. Yeah. And the thing is that these discrete time crystals, they are just on the verge of being barely simulatable by our classical methods, but for example, if you add noise to them, then it's already getting very difficult to simulate these systems. And so this is, for example, something that I think in the future will be very promising to look at more, is trying to look at such time crystals and maybe also ways to, for example, stabilize these time crystals on quantum computers. Yeah. So that is, let's say, the directions that are looked into when we talk about the non-variational results. Now, on the other hand, there's this whole, let's say, game or this whole idea of using these variational methods, like, for example, the variational quantum eigensolver. And the idea of the variational quantum eigensolver is that it really you have this function that you want to optimize, be it, for example, the energy, and this is then evaluated on a quantum computer, and then you optimize it classically. And it was shown that with this, you can, for example, reach or you can, for example, describe small quantum magnetic systems, like those systems that I actually investigated back in my PhD. But the problem is in these methods is twofold. On the one hand, you have a highly dimensional optimization problem in front of you. So that is something that you need to treat with your classical computer. And if that problem is not well behaved, then you can end up, for example, in local minima or in something that is actually not good enough to be for example, competitive against other classical methods. And the other thing is that it requires a lot of measurements. Yeah, so you need to really measure at each optimization step. You need to measure a lot of observables in order to measure your energy and then to make a step towards the right direction. Yeah, and this is why I'm a little bit skeptical of these variational methods. Although I myself have developed, for example, a variational or two variational algorithms, not in order to find the ground state, but rather to find these time periodic states. Yeah, so you can also use variational methods to solve, for example, the time dependent problem as well. Yeah. And that is so. There, for example, it's a lot less clear, I would say, whether we really find, let's say, or if this is really sustainable in the long term when we use more and more qubits. It's not so clear whether these variational methods will continue to work there as well. That's a little bit of an open question.
So yeah, so do you think that with logical qubits that would be different though?
I mean, there's a good statement. I don't know who said it, but I mean, all the algorithms, be variational or non-variational algorithms, they don't care about, or they inherently work on a logical as well as on a noisy quantum computer, right? So there are one or two exceptions. There are actually algorithms that was proposed that say that if you have noise in your device, then this helps. But to me, that they are a little bit special cases. But otherwise, all the algorithms so far that we have looked at are algorithms that that work on both. They work on noisy machines as well as on, let's say, perfect machines, on error-corrected machines. And once we have an error-corrected machine, then I don't need the VQE, for example, anymore. Or let's say it's maybe the VQE is something I can still use, but there, let's say, if I have a fully error-corrected quantum computer, it might be that I can just replace certain variational methods with, for example, let's say trotterized methods, for example, such that I don't need to suffer from this highly optimization problem that I need to solve on a classical computer. Yeah. So in that sense, I would say that in the end, all algorithms are quantum algorithms. They run on both devices, but whether I would use them on both devices, that's a different question.
Okay, so for business people who are listening, maybe, because some of them listen too.
Yeah, absolutely.
So how would you compare, what are you looking to accomplish in scientific research, which is important? And I like to point that out, that not enough people are using quantum computers for quantum physics, right? So
yeah.
what do you look for there compared to like what this type of work might yield in the more like practical application to, optimization and things like that.
Yeah, so I think that quantum simulation itself has a lot of industry applications, right? So if I think about material science, for example, there's a lot of things that are not simulatable with classical computers, and where, for example, a quantum computer might help me to understand certain kinds of materials much better. Right now, many kinds of simulations are based, for example, on molecular dynamic simulations, and if I can go down one level and say, wait, what about the quantum effects? Can I treat them as well? Then it gets, of course, interesting to various kinds of industries, be it chemical industry, be it pharmaceuticals, and so on. So in this realm, definitely, this can have an impact. It might be a little bit down the road, so to say, right? Because depends also on how well we, for example, develop algorithms for these devices. But I think in the long term, it will be something that will have an effect in these industries as well. If we think about material science, where it comes to quantum functional materials, then we're on a much closer road, right? So if we think about, for example, materials for metrological applications, now quantum metrology, for example, where I want to sense something on a much higher precision than before, then it helps to have entangled states, and these entangled states, for example, I can understand much better with a quantum computer, right? So if I say, I want to have a quantum sensor and I want to have the best entangled state on there such that it can detect, for example, a magnetic field with to a much higher precision, then I can simulate that entangled state on a quantum computer, and this will then immediately affect the performance of my sensor. Right. So, and with the sensor, if I can detect, I don't know, broken wings on an airplane, talking about things
Lots
that
of
are broken.
plane worries in the news lately.
Exactly,
so.
right? So if there is something that can detect this much more efficiently, I mean, that is worth something, right? That is really something that can change a lot in quantum metrology. On the other hand, I also draw a little bit of a big picture of quantum simulation in the whole field of quantum technologies, right? So this is kind of the, let's say, more opinionated piece or opinionated part of this article, is where I say, what role does quantum simulation actually play in this whole realm of quantum technologies? And to me, what quantum simulation does here, it allows us to understand quantum matter and technologies on a much better level than before, which could then lead to, let's say, spin-off applications, be it topological qubits. Maybe I can find topological qubits by simulating them first in a better way, and then I realize, oh, look, this material is actually a topological material and it hosts topological qubits. Or if I talk about spintronic applications, for example. So spintronics has the idea of using spin degrees of freedoms in materials in order to, for example, do ultra-fast manipulation of classical data. So this is something that we still need. We still need to do a lot of simulations with classical data. And if I can improve our classical devices by going from, for example, ferromagnets to antiferromagnets, this means that I would change the typical frequency with which they work from gigahertz to terahertz. And everyone knows what a gigahertz is. And if I now tell you, oh, your disk drive will be 10,000 times faster by switching to terahertz, oh yeah, that's an important information for all the big data guys out there, right? So that's something. Oh, that's a fast hard drive. Yeah, we could use that in AI, for example. And then on the other hand, if we have these technologies, these quantum technologies, they can, on the other hand, then enhance, for example, our quantum computing platforms, right? So far, we still have our problems with noise in these platforms, with scaling them, and so on. So if we can improve these devices by finding better technologies based on quantum simulation, then I can do better quantum computing, which on the other hand then enhances the quantum simulation part that I want to do on these devices.
That's what I was going to ask you next. We've come a long way since Feynman, And I was going to ask if you see this as like an infinite loop now that we might enter, where the quantum computers improve quantum computers and back and forth.
Yeah, that's exactly the kind of picture that I have in mind. Is because I mean, right now what we're using in these, for example, look at the superconducting devices. They're using aluminum based superconductors. And they have problems, right? They are amorphous materials. Due to these amorphous nature, they get, let's say, defect states in there that are talking to the qubits. Yeah, these are the famous two-level systems that are talking to these qubits and are ruining hours of measurements, right? Because suddenly there was this two-level state that appeared out of nowhere, and suddenly it's gone again. Yeah. So if we can use better materials there and understand quantum matter on a better level, then I can design, for example, engineer new kinds of quantum computers based on these new materials, right? And the idea is a little bit that we need something to get this quantum computing circle starting. And the reason is the following. If you compare this, for example, to Moore's law, what was the reason why Moore's law worked so well? By the way, so Moore's law, just to a reminder, is the law that in classical computing, we roughly get a doubling of our processing power every 2 years. Now, this was roughly the statement that Moore did, and this was based on the fact that our classical circuits are miniaturized in the same speed, right? So we get smaller and smaller length scales, such that I can do more and more computation on the same die size, so to say.
Squeeze more transistors.
Exactly. Squeeze more transistors in there and get more out of it for the same cost, so to say. Yeah. Mm-hmm. And the thing is that Moore's law, we cannot convert that over to quantum computing. Let me give you a very simple reason for that. Trapped ions, for example, they work with single atoms as their qubits, or single ions as their qubits. I cannot miniaturize an ion anymore. No. It's one ion and that's it. Yeah. So this approach that I had in classical computing, this doesn't work for quantum computing. Yeah. So it's not just about the miniaturization. No, it has to be another concept, so to say. And what I think is this other concept is that quantum technologies kind of self-improve by improving our knowledge about these systems, and thereby trying to get this circle of technology running. And this could then be really the driver for quantum Moore's law, that has a continuous improvement of the quantum computers in it. And I think here quantum simulation plays one of the main players, or is one of the main players, because only with quantum simulation I get this understanding, this better understanding of these devices and these materials and so on. And so that would of course be a whole new industry, right? So, but that is, let's say, speculative.
And I always laugh when I see in a movie that someone shrinks down to the quantum level. It's like, and what exactly are you made of right now?
Exactly.
There's nothing smaller, so I don't know what your little particles are made of right at this moment.
This was Ant-Man, right?
It's like that.
I saw that movie and I also thought, maybe not so much, but it's a nice try.
But it's a good point that because we can't miniaturize these things, that we're going to need other ways to double performance or whatever.
Exactly.
Forward. And on that kind of like sci-fi note, and also I guess tied in with your work with Space Agency. So people are familiar with the quantum many-body problem. Maybe if they've experienced tensor networks, it comes up there. Some other places. But they've also heard of a different kind of many-body problem with actual giant bodies, like the classical three-body problem.
Yes.
And that's getting a lot of headlines lately because of the Netflix show based on the amazing books.
I saw it as well.
Yeah, it's terrific. So I have to ask you, because people probably 1,000 times during this podcast have been wondering, can any of this be applied to, the Proxima Centauri system, something like you got a couple of stars and a planet. Can this improve any of our understanding of something like that?
It's great that you asked that, because I actually have two comments about one comment about your question, one comment about the series, because I think the series is great. So let me first answer your question. Indeed, there is a connection there, and the connection are so-called few-body quantum systems. So few-body quantum systems are like, for example, the planets orbiting the stars and so on, in that it's not so many bodies, it's a few particles, but already this few-body problem, because if it's in continuous space, right, so if it's not in a crystal, but if it's in continuous space, this quantum problem is also actually very hard to solve with classical HPC methods, right? And my good colleagues at the in DLR at the Institute for Quantum Technologies, they actually also look into this and looking into few-body problems, which are really related. So, for example, the quantum mechanical three-body problem is also very complicated. It's not solvable analytically, as is the three-body problem of the classical mechanics, so to say. Then let me give a second sub-answer to you. The other thing is, of course, that if we look at cosmology, if we look at high-energy physics, for example, trying to answer, okay, if we look back at the what happens if we're close to the Big Bang, right? Then quantum plays a very big role, actually. Yeah? So the quantum laws of quantum mechanics play a very important role in the sense that we have very dense matter and it's interacting. So it's a many-body problem that we're looking at here. And doing simulations in these kinds of environments is very difficult, right? So if we look, it's the same thing if we look actually at the atomic nucleus in trying to derive, for example, quantum states in quantum chromodynamics, which describes atomic nucleus, it's a quantum theory, it's a quantum field theory, and it's a strongly interacting many-body problem. And so you see there are all kinds of connections to the smallest, which are the atomic nucleus, to, okay, what if I have the Big Bang and I have very dense matter there, and this is also a quantum theory or quantum problem that I need to solve. So, but I know a lot of good colleagues actually who are coming from high energy physics, for example, that want to answer these questions, and they try to do this now with a quantum computer. So it could have an effect on our knowledge about the universe as well, which would of course be great, right? So this is really something I'm looking forward to. And the other comment I would have on the series is actually the series is great. It just depicts one thing as really strange. As you know in the series, in this Netflix show, what happens is that the accelerators, the particle accelerators, are doing something completely strange, right? So yes. And then the physicists are all like, oh no, now I'm losing my job and so on, right? So they're all super worried, yeah. And I think that the thing is, if this would happen in real life, the reactions would be the exact opposite. Because what a physicist would say then is, at that moment, is, I don't understand this. This is great. This is something new. Oh my God, right? I want to understand this, and new stuff is happening. Oh my God, that's the greatest thing that can happen to a scientist if he gets data that he doesn't understand, right? That's something to learn. Yeah. That's the moment where I say, great, now the work starts. Now I can think about this and why this happens and so on.
But it would be a dead end because they were messing with the devices. Yeah, to keep absolutely us from progressing scientifically.
Yeah, absolutely. They try to stop us, but I mean, in the end, I think in the show it's shown as they are trying to stop us, but in reality, I think they would actually help us indirectly by showing us what is possible to do, and therefore it kind of blow our minds and try to do something new that they haven't even thought about. So in that sense, I would think that actually they would help us in real life if we would get such crazy new physics that we can examine and have a look at, right? So that's the funny thing.
My final thought on the show is instead of like building games to train people and simulate like what's going on and flee your world and spend 400 years in space, maybe they should have just built a quantum computer.
Yeah, or that.
Yeah.
Solve
that
problem.
A simpler solution. I know, but that's really simplifying it. But you never know. It might help them understand the perturbations better. And it's funny. It's funny that it's just like never mentioned.
No, it's true. Yeah, that would be nice. Yeah, true.
Yeah, they do. So thank you so much for digging into all this work with us here. And I'll be linking everything in the show notes so people can check out your work. And yeah, hope to talk to you again one day in the future.
Thank you so much. This was very nice.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. The quantum many-body problem is the challenge of simulating quantum systems with a large number of particles that interact with each other. As the number of particles increases, the computational overhead of simulating such a system increases exponentially. As Feynman noted in 1981, to simulate such quantum systems, we need a quantum device. And we've done so with analog and digital approaches. Analog quantum simulation has shown an advantage over classical computers in that it tunes a physical device using trapped ions, cold atoms, or other elements, and represents a desired quantum system being simulated. However, there are still limitations to analog approaches. Digital quantum simulation hopes to simulate systems that don't fit on an analog device and which evolve over time in steps implemented using gates. This is more what you think of when you think of a quantum computer. Digital quantum methods include variational and non-variational methods. Variational methods are robust against noise in the NISQ era and use a combination of classical and quantum systems in a feedback loop to minimize a system's energy and get an optimal answer. Non-variational methods rely on discretizing the time evolution of a Hamiltonian and can handle a system's real-time dynamics. Of course, we're still limited by qubit counts, circuit depth, and noise, but regular listeners know we're making a lot of progress in all these areas. What can we do with these simulations as they improve? Quantum simulation can improve quantum sensors by simulating entangled states and enhancing their performance. In cosmology and high-energy physics, quantum simulation can help us understand the universe and solve complex many-body problems. Perhaps most important to QIS, quantum simulation may play a crucial role in advancing our knowledge and driving the development of better quantum technology. And, as we half joked on this episode, a quantum computer might have been all the aliens in the three-body problem needed to save their world. That does it for this episode. Thanks to Benedikt Fauseweh for joining to discuss his work. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.